us get into a little more detail, because we motivated ourselves into this requirement, right. Response time, jitter, bandwidth, redundant communication channels, and we divided this whole system into very broad areas. Engine compartment, we called it the powertrain part, then there is the chassis part, and then there is the body part. So, powertrain, chassis and body. So, we have to know a little more in detail about this powertrain itself. See, this powertrain is a very complex control law that is running inside. Okay. So, there are very complex control laws. Sampling is happening at millisecond duration, because it is all to do with engine rotation and all of that. So, you need a microcontroller which has very high compute. You must have OS or whatever software that is running to do multitasking. You will have to meet stringent time constraints as well, which means that the powertrain is a critical part there, and which has certain quality of service requirements, which perhaps is highest requirements highest. Equally high is the requirement from the chassis part. This is the chassis part. Okay. But what I have done is I have tried to show you that the powertrain cannot work in independence, it cannot work in isolation, it has to work with the chassis domain. And the chassis domain itself, as I mentioned, ABS is there. Let us look back at what all are there. In the suspension is there, steering is there, braking is there, all of that is part of the ABS system. Also ESP, I never elaborated it too much to you, but indeed ESP is the electronic safety program, which some of the current day cars seem to come with. See, again everything is moving in the autonomous part. People are building, manufacturers, vendors are building small modules, which will all of it culminate into a nice safe way of sitting inside vehicles. And please note, I keep repeating this, it is not that autonomous driving has come today. The whole traction towards building autonomous systems have happened over 30-40 years, right. So, and that is what we are trying to discuss all through. So, this ESP is interesting because it allows you to keep the vehicle on road. Think of a situation where there is a track and there is a big truck in front of you, and you are in your own way moving slowly towards that, and then suddenly from nowhere there is an obstacle here. Okay. You are going in your lane, suddenly there is an obstacle. So, the ESP program keeps the vehicle on the road by ensuring that it samples the condition of the road at something like 25 hertz, okay, 25 times per second. It keeps sampling using some sensor, realizes that there is an obstacle, and then commands back to the powertrain to cut speed and so on and apply brake or keep it on the track. In fact, cut speed in a manner that it does not skid. When the steering is swiveled, when you swivel the steering just to avoid the obstacle, you are often at such a high speed that it may turn round, or you may have a collision, you may have a dent, it can lead to any dangerous situation. Even if you swivel with the steering, the vehicle tends to put the car on the road, put the vehicle back on road in a manner that it is safe for people inside. So, this ESP is a very interesting program. Alright, so if you so this is so it has certain constraints, it has certain requirements when you talk about that. So, you will essentially be talking about chassis functions are indeed very important and as important as the other one as I mentioned. So, essentially more critical from a safety point of view, this is very important. Chassis, which I wrote here, this is more critical, I would say more critical from a safety point of view. All these ESP programs which are part of the chassis indeed gives you that feeling that it is very critical. So, in summary, powertrain and the chassis both operate in closed loop. This is so important to understand. It really operates in closed loop, and this is indeed a closed loop. I would say it is a closed loop control system. So, if you are familiar with controls, you will find it exciting to work in this area, and everything is moving towards time triggered and all that. Then there is the other one which is all about the dashboard. Then you have wipers, I mentioned to you about wipers, then lights, doors, seats, mirrors, you name it, which are all part of climate control. These are all software based systems, part of the body, climate control, AC and so on, right, AC parts, blowers and ACs and all that. They all come under the body part, and they are all mostly software controlled, and they exchange small pieces of information among themselves. Okay. They have numerous functions, but they exchange plenty of information, many exchanges of small pieces of information. Not all nodes require a high bandwidth. You can design low cost networks for this systems, and you can put them under a low cost network like LIN. Okay. LIN is local interconnect network, local interconnect network. Okay. So, most of the body related things will have a LIN network, but whereas powertrain and chassis will have a CAN network. So, you see what we are trying to show you, what we are leading to is that while you are going in for a away from the point to point systems to shared communication based systems, because you want to reduce the weight due to wiring, harness and all that, put them into a bus systems, a single bus is not going to work for you. A single protocol is not going to work for you because of this requirement. Which requirement? This requirement. Response time, jitter, bandwidth and redundant communication channels. If you put them in the forefront, you will say I can't do this with this protocol, but I do not need this for this requirement. So, if you match a requirement to what you want to achieve, you have a requirement and what you can put there on the vehicle, then you will have to necessarily design multiple protocols, and that is why the fact that a vehicle has a LIN protocol comes into picture. So, here we will get into the detail of the LIN. One node which is termed as the master possesses an accurate clock and drives the communication by polling other nodes. So, there is a master, this is a master slave paradigm. Master holds an accurate clock, okay, and drives the communication by polling the other nodes, which are essentially slaves. You poll them periodically, okay. These are slaves and this is the master, and then you start periodically, and then the mixture of different communication channels is now very clear motivation. Somehow you may also want to interconnect, right. On the one side you need a different network, but you may want to interconnect and then integrate these subsystems. So, all of that you would do by mixing LIN with CAN on a backbone. CAN plus LIN can happen only by at the backbone level, okay. So, you will have multiple networks, all of them connected at the backbone level. I will tell you in a peculiar way why you need to interconnect this, okay. For instance, if a door is open door is open, let us say, door is open, you may not want to start the engine at all, which is part of the powertrain, or you may not want to release the brake if it is part of the chassis. So, unless you have an integrated solution, ECUs talking amongst themselves, but each one of them having their own specific requirements, this is not going to give you a full solution, it will not give you safety. Therefore, if you ask yourself a question, door is open, what should you do? The ECU simply signals that a door is open, and then the powertrain ECU says I am not going to allow this car to start. Now, the chassis may say that I am not going to allow the brake to release, the brake will be on and the vehicle cannot move till the door is closed. You can have that safety consideration. So, all these things essentially mean these ECUs have to communicate amongst themselves. That is a very important thing. All of this leads to different types of classes of networks. You will have something called class A, which is multipurpose and which is essentially very low data rate requirement, okay, something like 10 kilobits per second. Then you will have class B networks. These are typically 10 kilobits per second to about 100 kilobits per second, and these are also non-critical, I would say, non-critical. This is anyway non-critical, this is non-critical, okay. Seat control, door lock, okay, all of them need some low cost technology. Then you can have class B. Between ECUs you may want to exchange data, and they will essentially be 10 to 100 or 125 kilobits per second, and they essentially use low speed CAN, okay. You can be using low speed CAN. So, they are essentially, I would say, for gluing between class A and the class C, okay. Supposing you have another class C, class B is more for gluing purpose. So, I will say between ECUs, between ECUs. So, when I say ECU, I mean electronic control unit, okay. If there are multiple electronic control units, communication between them is something which you can use with 10 to 125 or 100 kilobits per second, but it is still non-critical. It can also be for gluing between classes, because it is essentially between ECUs, not necessarily within the same class, but also across classes. You will have to see what a careful decision, how you make this careful decision, but what should be connecting at what rate, what ECU should be connected at what rate between them. So, then there is class C, right. So, the class C essentially real time, and you are looking at, so if this is 100, I will say this is at 125 kilobits per second to about 1 megabit per second, 1 Mbps, up to 1 Mbps or so. This is high speed real time, high speed real time. Then, so that is what you would say, and then there is class D, which is more than 1 Mbps, greater than 1 Mbit per second. This is high speed real time CAN, I will say here, and then associate this with powertrain and chassis. This is greater than 1 megabit per second, and this is mostly for multimedia, right, multimedia, correct. And they use another protocol called MOST here. MOST is another protocol, media oriented system transport, MOST. So, that is going under class D, very high data rates, okay. Sometimes you may also want to use this class D for safety critical, applications. Currently you can say that they are mostly centered around class C and class D. Most of the modern cars are under either class C or class C, but not the lower side. It has to be around the 1 Mbps range for all safety critical applications where you need predictability, fault tolerance and so on. All this you will be using higher. So, here actually you will talk about another protocol which is FlexRay, MOST and FlexRay. FlexRay also comes here. What is a good example today? Look at Volvo XC90. It has roughly 40 ECUs interconnected by LIN bus. Okay. There is also a MOST. You will see a MOST, you will see low speed CAN, okay, that is here between the class C around the 500 kilobits per second to 1 megabit per second. You will see a CAN, low speed CAN. You will also see a high speed CAN, okay. All of that integrated into this vehicle. Is that it's reality that such networks exist inside a vehicle. So many ECUs exist, so many different type of protocols exist inside a very complex system, complex protocols, many protocols. All of that, if you slowly start dissecting, you will realize that there are good possibilities for inserting your algorithms by using different sensors and move towards the autonomous vehicles. So, now that we rooted ourselves into these three broad I would say domains of a vehicle: powertrain, chassis and body, right, all the three, we did not yet answer, at least to design any system that we need, what are the latency requirements of these systems. So, you have to answer this because we started with those QoS parameters of interest. So, I put down a small chart here which will help you to do that. Powertrain, what does it do? It controls the components that generate power, and it does do that, it converts that into transmission on the road, and you are talking about 10 microseconds, but not so much of any great bandwidth requirement. Latency is important, end to end latency is most critical here. What is the chassis requirement? What does it do? It controls the steering, it controls the braking, okay. I mentioned to you about ESP, then I also mentioned to you about active suspensions and so on. This also, there is no way by which it should be anything less than the first one, right, because they are equally important, and also the bandwidth requirement is quite low. Look at body. Body is not a problem really. You have radio, you have climate control, climate, I will simply call it AC, then you have seats, lights, okay. All of this, yeah, it can be anywhere up to about 10 milliseconds perhaps. You do not care so much, and it also has a low requirement. These three sort of give you an overview. Then if you are now going towards autonomous, okay, this is what we know very well. If you want to do driver assistance, okay, and you want to do safety, driver safety, which are all coming up now, okay. So, these are all controls designed for increased safety, controls for increased safety. It should all be in the order of 250 microseconds. Okay, you can do it in about 250 microseconds, and you will need 20 to about 100 megabits per second per system. Okay. These are all different sensors which you are going to put, and you obviously need a lot of time to sort of process that signal and give it to you in less than 1 millisecond, right. So, it is 1/4 of a millisecond. Essentially this is a sufficiently high requirement compared to what you see here, which is 10 microsecond. This you can say is running at a much slower loop. The driver assistance and driver safety is running at a much slower loop, okay, because it is looking at safety. It may have sufficient margin to decide, because if you are putting a camera system, it has an ability to look ahead, to look in the night, to look and take action and provide you a feedback. That feedback loop is typically in the order of 250 microseconds. Once the feedback comes, which broadly falls under the domain of driver assistance and driver safety, the actuation will happen via the powertrain, which in which case it will go back to 10 microseconds. And these are add-ons which can run at a slightly slower loop, but once detected we will have to give commands to the powertrain, and the powertrain itself will have to have a latency of less than 10 microsecond from the time the command is issued. This driver assistance is not slower compared to powertrain. These are the basic requirements, and this is an add-on that you have put. The add-on has to compute and give you in some time, and that will have to in turn go back to the powertrain, because ultimately driver assistance or whatever you do in terms of your algorithms, the actual mechanism will have to fall under powertrain or chassis only, right, and they will have to have very stringent latency requirements. If you do HMI, human machine interface, okay, this one controls displays, okay, and other interfaces. This is controls displays, and other interfaces. With the driver, passengers and all that, and this can be even in milliseconds, in the order of milliseconds. So, you can now sort of summarize the different buses which are there part of this of a modern vehicle. CAN gives you anywhere up to about 1 Mbit per second. LIN can give you, as I mentioned, not more than 10 to 20 kilobits per second. Most media oriented stream transport 20 megabits per second. Right. Then flex ray, you will get 10 megabit per second. Then you have time triggered protocol and TT-CAN and all of that. Okay, I think for completeness it is good to put 25 megabit per second, and TT-CAN also gives you time triggered CAN, which gives you about 1 Mbit per second. Much more interesting TT-CAN compared to other protocols. So, in summary, these are all running inside a vehicle. Okay. We will have to see how exactly we can use these things and design your algorithm. So, where do your algorithms come in? Where is the space for algorithms? The space in for algorithms is depends on what sensor you are likely to put. For example, if you take this ECU, okay, if we concentrate only on this ECU, we have to come up with some way of detecting some anomaly. You may want to do an anomaly detection in the engine ECU. This is the engine ECU. This is the engine ECU, right. So, and then this is the OBD port which I mentioned to you, and somehow you should be able to read off these OBD codes, okay. PIDs, they are called PIDs. PIDs are also called parameter IDs. Parameter IDs. The parameter IDs are fixed as per a standard, but manufacturers can add their own PIDs as well. We can get into that detail when we go into OBD too. But the scope for your algorithms is out in this space. If you are indeed looking at the engine ECU, how do you connect everything back? You have to look at the powertrain, and you have to look at something that happens in the reaction time of the order of 10 microsecond or so. Anomaly you should detect quickly, and moment the anomaly command is given to the powertrain system should respond in less than 10 microseconds. So, let us see how we can do this in terms of a simple example.